Hey, welcome to Chapter 9. I have been working on the PowerPoint, modifying a few things. So what you're going to see is that the section about the atmosphere has a lot more detail than the sections after it. I'm just kind of running out of time since I need to get this recorded before I have to leave. Um, so take a look around you at all this air. Wow. So we're in this ocean of air. And just as we're no more aware of the air around us usually than a fish is of the water around the fish. But the atmosphere is very, very critical to life. Obviously, we're breathing all the time. And as I mentioned in about magnets, the Earth being one big magnet, and we have this big magnetosphere that extends around us that has protected us from solar radiation that would have stripped away our atmosphere. So one thing about our atmosphere is that it's pretty unique that we have an atmosphere. And our atmosphere didn't start out as it is now. It's quite a bit different than 4 billion years ago. When the Earth first formed, it didn't have an atmosphere that was anything like the current atmosphere, and certainly none of the life of today could have survived in that kind of atmosphere. And in fact, living things created the conditions for more living things. And I want to talk about that a little bit. Um, so the lower atmosphere is where all life is, and that's where the oxygen is. That's where most of the gases are. The gases do have mass, and they are attracted to the center of the Earth by gravity. And so the most gas is close to the surface, um, just because of gravity. And so we'll talk about different layers of the atmosphere, but realize that the most gases are just right around the surface of the Earth within the first several miles. And come on to the next slide, please. Okay, so we have about 80%, 78% nitrogen and about 21% oxygen. Oxygen is what we and all other animals are using to drive our cellular functions. You eat and breathe both for the purposes of generating chemical energy in the form of ATP. So I'm not going to go into ATP production right now, but without oxygen, you're dead, right? And pretty much that's how you die. It doesn't matter if your heart fails or if it's some other way you get crushed by a bus or something. Ultimately, your cells die because oxygen stops getting delivered to them. They aren't able to continue their metabolism. They're not able to continue using oxygen to make ATP. And you need to eat also. You can't survive just off of breathing. But you only need to eat periodically because you can store large amounts, a whole meal's worth of food in your body, and plus you have fat reserves and things like that. But you need to breathe constantly. You need to constantly replace the gases, and so you're breathing in oxygen, using that in your cells, specifically in your mitochondria, to produce ATP. And in the process, you're taking apart food molecules, and the carbon that's in those food molecules, it's ending up as carbon dioxide. So you're breathing out the carbon dioxide. Well, you notice that carbon dioxide is less than 1% of our atmosphere. So why is it that if animals are breathing out all the time, that there's so little carbon dioxide? It's because of all the plants. The plants are taking that carbon dioxide and they're using it to build sugar molecules. And then they're using those sugar molecules to build more complex things like cellulose and starch and stuff like that. So the plants are all competing for the carbon dioxide that we're breathing out, and that all animals are breathing out. And the plants are also producing the oxygen that we're breathing in, right? The plants, they take apart water molecules in a process called photosynthesis, and they take apart water molecules, they produce oxygen, and they are also using the energy of photosynthesis to put together carbon dioxide molecules into sugars. So this process of photosynthesis uses carbon dioxide, releases oxygen as a byproduct. Now let's go back several hundred million years before there was oxygen in the atmosphere. Photosynthesis started in the oceans with photosynthetic bacteria, and these bacteria started producing oxygen as a byproduct because they were able to do photosynthesis. But nothing was using the oxygen. The oxygen was just a waste product, and it was a dangerous waste product. So the oxygen would go out of the bacterial cell and into the ocean, and oxygen is very reactive, and it would react with something. And one of the things it reacted with very readily in the ocean was iron. There was iron dissolved in the ocean, the metal iron. And you know that iron plus oxygen, you get rust. Well, even dissolved iron, it was dissolved in the water, it would react with the oxygen, it would form rust, and this was a solid, and it would precipitate out, meaning it went from a liquid form, dissolved, to a solid, and so as a solid, it would sink down to the bottom of the ocean. And this happened for millions of years. The photosynthetic bacteria would produce the oxygen, it would combine with the iron would settle down to the bottom of the ocean. And over millions of years, it used up all of the iron that was dissolved in the ocean. And that layer of rust that formed over those tens of millions, hundreds of millions of years, at least tens of millions, I'm not sure. I think 70 to 150, I don't know how many millions of years, to use up all the iron. But that layer of rust is what we mine today. That's where our iron comes from. When we go get iron ore, it's from that time period. So the photosynthetic bacteria, then they kept on producing oxygen, and it started to just dissolve into the surrounding water, and nothing, and it was just started to build up, and it started to build up in the atmosphere. And as I said, oxygen is very reactive, and it can be a very dangerous molecule for cells. This actually wiped out most of the life on the planet at the time, which was mostly bacteria. But these bacteria at the time, they couldn't handle oxygen. It was too dangerous for them. Around this time, some bacteria figured out how to use that oxygen. And that's where the cellular metabolism that we're familiar with today came about, of using oxygen. And there are still bacteria that can't take oxygen. There's still anaerobic bacteria that can only exist like under the ocean floor or in your gut or in places without any oxygen. Other bacteria can tolerate oxygen, and still others have learned to use the oxygen. They've evolved the ability to use the oxygen. All animals use the oxygen. So anyway, that's an interesting thing about our atmosphere, and there have been other modifications over time, but the biggest was this oxygen revolution. And it's interesting too to think that all the wood, on the whole planet comes from, it was built out of carbon dioxide molecules being taken out one at a time by plants. And so all the forests of the whole planet have just come from that gas. And there used to be a lot more carbon dioxide in the atmosphere if you go back far enough, but the plants have sequestered it. And a lot of those plants, they die over time. That carbon dioxide goes back into the atmosphere, or if you burn it, it goes back into the atmosphere. But large swamps during the time period of prehistoric times, large swamps and would get covered in mud. And they would just die down without releasing that carbon dioxide. And eventually that turned to coal and oil, and that's what we're mining today, is those carbon deposits from living things of hundreds of millions of years ago. So that's another cool thing, is that and it's a bit worrisome too, because we're releasing so much carbon into the atmosphere that hasn't been there for a long time, that it can change the dynamics of our climate, and people are certainly worried about the possibilities there. We won't ever be able to reach levels higher than what it's been in the past, but by increasing them to levels higher than what it's been in the recent past, it can change things quite dramatically. Okay, so oxygen, carbon dioxide is an interesting cycle. We're all animals using the oxygen, letting off the carbon dioxide. All plants and photosynthetic bacteria using the carbon dioxide, letting off oxygen. Plants do use oxygen as well, but they just produce a lot more than what they use. Okay, we've treated the atmosphere as a big sewer, a dumping ground for a long time. We just, put smokestacks up and polluted. One of the things I like about living in Del Rio is the clean air. And I've lived in some beautiful places, but the air quality can be really bad at times. So we're still polluting on a large scale. There's more I could talk about with that, but I'm going to move along to the layers of the atmosphere: troposphere, stratosphere, mesosphere, ionosphere, exosphere. This is basically how these are, they're not distinct lines, but they're kind of lines as you go from the surface of the Earth to outer space. And outer space is about 500 something miles. There's not a distinct line between the exosphere and where outer space begins. But it's kind of funny to think that it's only 500 miles away. You're in outer space. You can just point your car up, and you'd get there by tomorrow. But you can't do that, obviously. Gravity is a really hard thing to overcome. So let's just start with these. Now, the amount 0 to 10 miles, 10 to 20, 20 to 50, 50 to 500, 500 to outer space. These are approximate, and it varies depending on season and whether you're at the equator or up north, or so these are not exact numbers. But certainly know the layers from closest to farthest, and a few tidbits about them can be helpful. Troposphere, that's where we live. That's where everything lives. And it's where all weather happens, actually. All the clouds are in the troposphere. And so from the Earth's surface up to about 12 miles, someplace 23,000 to 50,000, 60,000 feet. Like I say, it varies a bit. And I mentioned gravity and how the molecules are attracted to the Earth. They have mass. The Earth is a giant mass. They are attracted by gravity. So this closest layer has about 75–80% of all the mass of the atmosphere, all the molecules there. And oxygen, carbon dioxide, they're going to be heavier than hydrogen, helium. The nitrogen's heavy too. So these heavier ones are going to be closer. As you get further out, you'll see more hydrogen and helium, which are lighter. So here's a look at all the different cloud types, and you can see that most of the clouds that you see are below 6,500 feet. So most of the clouds that you see, it's not, it's within a couple of miles, a mile or 2 miles of the Earth's surface. Occasionally you'll see giant clouds that go way up and have an anvil top, and these can be pretty exciting, summer storm clouds. That very top, they're hitting the edge of the troposphere. They're hitting into the stratosphere. There's kind of a transition there, so they get flattened off. They don't go up into the stratosphere really. Now, commercial planes will try to fly above all the weather. So they'll cruise, 30 to 50,000 feet to try to get above all the weather, because in here you've got all sorts of turbulence that goes on. There's a lot of mixing of warm and cool air, and a lot of winds going this way and that way. A lot of up and down stuff that the commercial traffic tries to avoid. So the stratosphere is the next layer up. Commercial jets, like I say, can fly in the lower stratosphere. They can't go too high because they still do need oxygen for their jets. And in the stratosphere, we got about 20% of the mass. So in other words, above the stratosphere, there's very little mass. There are very few molecules of the gases. So the stratosphere gets its name because it's stratified. Okay, it's stratified. Now, for the troposphere, as you go up in elevation, it gets colder and colder and colder and colder and colder and colder and colder. Right? The further up you go, the colder it gets. But within the stratosphere, it's the opposite. The warmer layers are up high, and as you go down, it gets cooler. And that has to do with the fact that it's absorbing ultraviolet radiation in this area, and that warms up the upper layers. So the stratosphere is very important for keeping us alive, because this is where the ozone is, which is oxygen. usually two oxygen molecules are together. It's O2, right? That's oxygen gas, O2. Ozone is O3, which is kind of weird, and it's not very stable. But these oxygen, I think it's mostly, ozone's mostly formed in the stratosphere as the oxygen absorbs the ultraviolet radiation. And the ozone is a protection against UV radiation, and it was a big concern. We were losing our ozone layer due to chlorofluorocarbons that were used in all sorts of propellants, these cans that we're spraying and refrigerants for our home. And so worldwide, we eliminated chlorofluorocarbons, and luckily the hole in the ozone layer has been closing back. We kind of saved ourselves on that one. For a while, that hole was getting big enough that in certain times of year, the hole in the ozone layer would pass over southern Chile or Australia, and they were getting big increases in skin cancer due to the extra UV radiation that was coming through. Okay, another thing about the stratosphere that's worth talking about is a man named Ionosphere. He's an engineer, senior vice president of Google. He's a well-known computer scientist. He didn't tell people, not too many people, that he was doing this. He worked on it secretly for a few years, and then 57 years old, he puts on this 235-pound spacesuit that he and his team have designed, attaches him, and he's got a whole life support system in it, attaches himself to a giant weather balloon, floats up into the stratosphere. So he went up about 25 miles up. Took 2 hours for the balloon to go up, 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 and then he detached himself. He pushed a little button, a little explode, and so he's falling. The ride down took 15 minutes. Now, most of that 15 minutes was after he pulled his parachute. He could have waited a little longer, but he had a very fast free fall. He got up to something like 822 miles an hour. Now, he broke the sound barrier in his fall, so there was a sonic boom with him coming down, and it wasn't just him screaming really loudly. Anyway, so he broke the record. Previous record was set by a daredevil who had millions of dollars in sponsorship and made this big show of going up in this special craft and jumping, and that was really cool. And then here comes this Google engineer who, without much fanfare and without external funding, he beats the record. So he did get up into the stratosphere. There's his giant weather balloon with him attached to it, going up. And here's a look. He's not closed up in his spacesuit here, but it's a big spacesuit. There it is, closed up. This is as he's parachuting back down. So the highest a person's ever gone in a balloon, the longest free fall, the fastest free fall. 822 miles an hour, I think. So he broke several records there. Kind of crazy. Mesosphere. Mesosphere, I don't have much to say about the mesosphere. It means the middle atmosphere. And aircraft can't go here. It's above the aircraft max out someplace in the stratosphere. Depends on the aircraft. And little airplanes, they stay in the troposphere. Commercial aircraft into the stratosphere. Military aircraft, some of them high stratosphere, but nothing gets into the mesosphere. Most balloons can't get into the mesosphere. There are atmospheric tides going on, big east-west. I don't know too much about it. Extremely cold, can get minus 226 degrees Fahrenheit. So it starts someplace about 30 miles up, and it's kind of a range. Go back to that other slide to see the better numbers. But here's a view. Now, it's a little bit misleading because the shuttle is way up above any of these layers. The shuttle is just kind of framed in this picture. I assume it was taken from the space station or something. But they're looking, back at the Earth. And this is the troposphere in orange. So that's a nice clear picture of the troposphere. And then here's the stratosphere in white. And so you can see that there are distinct layers here. The troposphere, and then there's a very clear edge before you get to the stratosphere, and then into the mesosphere. And I assume this is kind of the edge of the mesosphere up here, which puts us into the ionosphere. And it's called the Ionosphere because the atoms that are there, they get ionized by the solar radiation coming in, meaning they get an electron, added to them or taken off, and so they have a charge to them. And I think it's the ionosphere, or maybe just past it, where the aurora borealis, the northern lights, takes place, and that has to do with when there's a solar flare, which is basically the sun burping, huge amount of solar radiation going out, and it's interacting with all these atoms up in the ionosphere, and they give off light. So that's the northern lights. Shortwave radio bounces off the ionosphere, so that allows for communicating with shortwave clear across the globe, and it is affected by the solar activity. And there's one other tidbit I wanted to say about the ionosphere. Totally forgot it. Shortwave radios. Oh well. I said then it's outer space, but well, there's still the exosphere, right? So the ionosphere, we don't have very many gases at all. Those that we do get ionized. The exosphere, you still have some gases. Basically, this is saying, well, it's not really an atmosphere, but there's still some particles that are attracted to the Earth. They're not quite, someplace in the exosphere. Some of them are going off into space. Some of them are falling back down into the Earth's atmosphere. So they're kind of bound by gravity, kind of not. And there's so few gas molecules floating around that they rarely even bump into each other. Down here around me, the molecules are bang, 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 bang. They're bouncing into each other like crazy, constantly. Up there, they're just it's mostly empty space, and the exosphere just kind of, there's not a clear boundary, where you say, okay, now we're in outer space, but that's where it goes to. Okay, a little bit about water and the hydrologic cycle. Water is the most abundant molecule, would you say, on the planet? Well, I don't know. 70% of the Earth's surface is covered with water. Oxygen, now let me jump ahead a slide and then come back to this. If you have a glass of pure water, it's just H2O. That's one oxygen for every two hydrogen. So it's a third oxygen, 2/3 hydrogen. But oxygen is a much larger atom than hydrogen. So here's one oxygen, and here are these two little hydrogens on it. And so by mass, the oxygen weighs so much more than the little hydrogens. So it's about 89% oxygen by mass. And if you go beyond the scale of our planet, look at the whole universe, it's mostly hydrogen, by far, mostly hydrogen. Hydrogen and helium together make up 98% of the universe. Hydrogen has one proton, helium has two protons. They're very small, very light. So this is basically, what was there right after the Big Bang? It was hydrogen and helium. But so 2% of the universe is everything that's not hydrogen and helium. So our whole planet, all the carbon, all the oxygen, all the sodium, potassium, calcium, iron, gold, whatever, all the heavier elements, that's 2% of the universe, to make up planets and things like that. So stars are mostly hydrogen, helium, including our sun. So anyway, so we say the most abundant element on Earth is oxygen. That's going by mass, because not, but if you're just counting number of atoms, hydrogen still wins. But if you go by mass, then it's definitely oxygen. Oxygen is a big component of sand. It's a big component of water. Water covers the Earth's surface. Water is absolutely necessary for life, and the properties of water are very important. We talked about them in another lecture. Obviously, we need water for building things. We need water for agriculture. The wealth of our country, we like to think of, oh, it's our technology, it's our military, it's our this, it's our that. You know what? It was our agriculture that was the foundation for why we are such a wealthy nation, because we had good soils and we had water. Okay, and it's another thing that I love about Del Rio is good water, good air, good water. Those, I like to live. Those are two things that are absolutely necessary for life. The hydrologic cycle is this recycling of water. Earth is not making new water. There's no new water coming in from space. We have new sunlight coming in every day. We don't have any new water. And so the water gets recycled over and over and over and over. And so when you take a drink of water, I promise you, there are individual water molecules in there that were peed out by Tyrannosaurus rex. There are individual molecules in there that Moses drank. And I can say that with some confidence because in a glass of water, how many trillions and trillions and trillions of water molecules are there? And they have been recycled over and over and over again. They are billions of years old. And, they might spend thousands and thousands of years in the ocean or thousands and thousands of years in an underground aquifer. But eventually, they get recycled. They get moved around. And so, it rains, obviously. The rain comes down. In Del Rio, we don't, it doesn't absorb. It just runs off very quickly. So we get this, short-term flooding. The rivers, so it goes quickly into the rivers, gets into the Rio Grande, empties into the ocean. Some of it, a little bit of it sinks down in, and across Texas, that which infiltrates the springs that come up in Del Rio, that water may have come from hundreds of miles away, but under the ground before it pops up at our springs there. So here it is in the ocean, then it evaporates. A lot of the clouds that are formed, it's from evaporation coming off the ocean. Now, where else does the water come from? It comes from plants. Plants are always losing water through their leaves. That's transpiration. And so coming from the plants, it comes off the soils, mostly plants. If it's on land, it's mostly coming out of the plants through transpiration. If it's over water, it's just evaporation. And, okay, animals contribute a little bit, like we sweat. But anyway, up it goes into the atmosphere, and it gets colder and colder and colder. The molecules move slower and slower. They start to stick to each other. They form clouds. If the clouds get enough water in them, they get too heavy. The molecules that start, the little tiny, tiny droplets start to stick to each other and form bigger and bigger droplets. Eventually, gravity overcomes them and they come fall into the earth as rain or snow or hail, things like that. So we're not really talking about weather, but just realize that this cycle, the water goes around and around and around. And we have to really take care of the fresh water that we have because most of the Earth's water is salty. 97% is in the oceans. So what do you have left? You have what's in the atmosphere, what's in the lakes and rivers, what's frozen in your ice caps and glaciers, and what's underground. And if you look at all the water for the whole planet, it looks like this. So this color is the oceans. Okay, there's the oceans for you. This lighter green here, this is the fresh water underground, and we've been using that up quite a bit in Texas and California. It's starting to become an issue because it takes thousands of years to recharge that, or it can take. Biological water, what's in living things, there's a very small amount. Atmosphere, very small amount. Fresh lakes, it's that kind of purplish blue right there. That's all your fresh lakes in the world. A little bit in the soil, ground ice, permafrost, and frozen in glaciers. So it's like, okay, where are you getting your water, folks? From this purplish square. You know, that fresh lakes, that includes rivers too. Fresh lakes and rivers, that's it. That's your drinking water pretty much. You know, you can pump, well, a lot of places you're pumping this groundwater, right? But I'm a little worried. We waste a lot of this too. We use a lot of it for fracking. It's mostly used for agriculture. But the Central Valley of California, they've been pumping the water so much that the ground is sinking dramatically. Some places the ground has sunk 2 feet. And, you know, as we deplete that groundwater, we just, you know, the well runs dry. You have to put the well deeper and deeper. And, you know, it is possible to use it up. You have to be careful. Okay, world oceans, I'm not going to say much at all. I got to wrap things up. Look, we have different oceans, and it's all one connected ocean. So we give them different names because they do have different traits and kind of, you know. So this is Atlantic Ocean here, through here, you know, between the Americas, between the New World and the Old World, so to speak, is the Atlantic Ocean. I know a guy personally. Actually, I know his son personally, and his son-in-law and his daughter. I've never met him, so okay, I know of him. Anyway, he rowed across the Atlantic Ocean. He's nuts, but he did it. It took him, I think, 3 months to row a very special rowboat that he had, and so we had to have, you know, 3 months of supplies on hand, and just a lot of stamina and a lot of time alone. 3 months, he was able to row across the Atlantic Ocean. Pacific Ocean is even bigger. So if you were to go from, you know, North America over this way to Japan, for example, that would be Pacific Ocean. Hawaii's out in this Pacific Ocean. So between, you know, on the western edge of the Americas, over towards Asia, Australia, that's Pacific Ocean. Indian Ocean is in this area. There's India there, Australia, Africa, this section here, Indian Ocean. We have an Arctic Ocean up around the Arctic, the Southern Ocean around the Antarctic. Okay, Pacific Ocean is the largest, about 1/3 of the whole total ocean surface. It's also the deepest, almost 13,000 feet. The Atlantic Ocean, about 1/4 of the Earth's surface, a little, not quite as deep, 11,700 feet. Now, the Pacific Ocean, the average depth is almost 13,000 feet. The deepest part is the Mariana Trench, and that gets 14,900 or something like that. I don't think it's 15,000 feet. I don't think. So the deepest part of the ocean is not as deep. I better check this just real quickly. Sorry. Deepest part of the ocean. Challenger Deep, located beneath the Western Pacific Ocean, southern end of the Mariana Trench, 36,200 feet deep. Okay, that's deeper than I said. So good thing I checked. So 36,200 feet deep is the deepest point. The highest point on Earth is 29,000 something feet in Mount Everest. And so what is that? 65,000. So from the deepest point of the ocean to the highest mountaintop is about 65,000 feet. And if you were to compress the Earth to the size of a basketball, it would be much smoother than that basketball. The deepest point of the ocean would not be as deep as the depressions on a basketball. The highest point on the ocean would not be as high, or the highest point, Mount Everest, would not be as high as the bumps on the basketball. If you had the Earth compressed to the size of a basketball, it would be a near perfect sphere. It would feel smoother than glass, and you wouldn't even be able to tell with your finger what was land, what was ocean. That is how small the Earth's crust is compared to the whole size of the Earth. So we're talking, you know, very, very thin layer where all this life is. And it also, having it in a perfect sphere like that really tells you a lot about gravity, how gravity really does bring everything down to, you know, to flat. So that's kind of weird to think about, but okay. Moving on. The Arctic Ocean is around the North Pole, completely covered by ice. There's no land mass under it. It's just Arctic Ocean. There's not a continent up there, as opposed to the South Pole where there is a land mass. There's a continent. Indian Ocean between South Asia, Africa, Australia. Um, Continental shelf and the slope. Okay, I'm really running out of time here. Continental shelf. Continents are on continental plates, so the part above water doesn't necessarily, it's not necessarily like this at the edge of the water. There's usually a shelf before it slopes off, and that shelf is shallow water. That's very productive because it's getting a lot of sunlight, and you have the base of the land underneath the ocean floor. That it's not deep, and so the corals can live here and the kelp and things. So the continental shelf is where most fishing occurs. It's where most life is in the ocean. Then you get to the slope, and then beyond that is deep ocean, and there's not nearly as much life out there. Um, so continental shelves are very important. There's some treaty between nations that says, I think it's 200 miles around your land is considered, your ocean, basically. And I don't know all the implications for that. Ocean currents, not going to be able to say, check out your book, but you've got very distinctive, these ocean currents, well, there are also wind currents that follow interesting patterns too. But ocean currents, they go in pretty distinctive, large scale turning about. And so the guy who rowed across the Atlantic, he was careful to get one of these currents. I can't remember where he set off, but he ended up, most of the time he was being carried the correct direction by the current. You don't want to try to row against the current. That would be terrible. One of the things that happens, some of these areas, you get kind of this circling effect. I didn't look for the garbage patch in the ocean, but it's pretty terrible. Some of the images that you see. So there's just some examples of, some of our garbage just gets accumulated in these big areas. It's pretty disgusting. The amount of trash that's in the ocean, and it can just take hundreds and thousands of years for it to disappear. The plastics are a particular problem, and they break down into smaller and smaller pieces. The whales are eating large amounts of plastics. Plastic bags. I talked to a girl who worked with sea turtles. The plastic bags floating around can look like jellyfish. A lot of sea turtles choking, or they die from eating too many plastic bags. Some of the albatrosses think that some of the garbage looks like food to an albatross, so they feed it to their chicks, and then the chicks die before they're able to leave the nest, and you can just you can see the chick dies and the garbage stays with it. There are lots of pictures of albatrosses full of garbage. So we do have to. We're becoming more aware. We're starting to change how we do things, but it's tough. There has to be social pressure to drive the change. Okay. Ocean currents are very important to commercial fisheries and so much more, but one more time. Ocean temperatures are not constant, and the temperatures are in part why there are currents. And things are going to be hotter towards the equator, colder towards the poles. This is going to create, current is kind of similar to wind. It's the mixing of hot and cold. And there are some long-term effects like El Nino, where the current kind of sloshes everything in one direction, clear across the Pacific Ocean for a few years, and then it comes back. And you might want to read up on El Nino a little bit. It's interesting to see the effects that it can have on weather. Soil, my goodness, I could talk for an hour on soil. It's not the dirt. It's the life that really matters. And we've been mistreating our soil terribly, I think, and just treating it as though the life in it doesn't matter, treating it like it's just the minerals in it that the plants need. But it's broken down rock, and it's not just the weather that breaks it down. It's the fungi, it's the bacteria. The fungi are able to basically eat rocks, to make acids to break it down, and it's the fungi and bacteria that make the elements available to the plants. They form symbiotic relationships with the plants. So man, go compost something. Encourage some life in your dirt. Get it back to soil. I know this area doesn't have a lot of soil. We got very little on top of that limestone. So the minerals are inorganic compounds in Earth's crust, meaning it's just part of the rock itself. It's not made by life, but it may have, you may need living things to make it available to life. You may need those bacteria and fungi to make it available, to get it out of the rocks and into the living systems. Oil, coal, natural gas, we group them with minerals because we mine them. They're not really minerals in the sense that they didn't come pre-made in the rock. They were made by life. I mentioned that, the swamps and stuff decomposing, and so oil, coal, natural gas, those are all products of life, just ancient life. Go back, I don't know, 60 to 300 million years ago. Living things, biology, all of life gets really exciting. We'll talk more about living things later. But it's a constant motion, life of, things being born, things dying, things eating each other, species evolving, species going extinct. Things are always in motion with life. And so conditions change, and species adapt, and species diversify, and species help each other, and species harm each other, and so the evolution of life on Earth is just kind of, it's almost, if you sped up geologic time, it would just be like fireworks, a whole bunch of species over here, and then they die out. A whole bunch of species here, and they die out. And we think, we are here, the dinosaurs aren't. Man, the dinosaurs were here for tens of millions, 60 million years, 100 million years. They had a long run. We've had a couple 100,000 years as a species, so don't get too boastful yet. Food chain, like the flower's producing something, and the caterpillar eats it, and then the frog eats that, and the snake eats the frog, and then the owl eats the snake. It's a little simplistic. A food web is more accurate, and even here, this is a little simplistic too, because maybe you should make these arrows thinner or thicker depending on, like, is the owl eating a whole bunch of mice and hardly any squirrels, or here you can't really say. And this is a very simplistic food web. A more realistic food web. Let's see if I can find one really quickly. Let's just look at food web. Most of them are going to be simple things. Let's see if we can find one that's actually more realistic, how things really are connected. No, not really. They're going mostly for simplistic. Here's one that's kind of more realistic. I'm liking this one better, except it's not coming into decent resolution, but just showing many more connections and how one thing might be connected to 100 other things. So, here we're seeing a mouse connected to a fox, a hawk, and a snake. Well, okay, but how many different species of plants is it connected to? And maybe the mouse competes with the birds for seeds. Maybe the mouse competes with some ants for the seeds. Maybe the mouse is affected by some insects that like to suck its blood. And there are way more connections than what we can represent reasonably. So it is a web of life, and when you pull one string, it's going to affect other things. we are in the 6th mass extinction. We've had 5 mass extinctions in the history of our planet. We are now in the 6th, and it's caused by us. It is a mass extinction in the sense that species are becoming extinct at about 1,000 times faster rate than the natural. Species do go extinct naturally. It's just that it's happening at a much faster rate. And it doesn't seem fast to us because we're working on the time scale of our lifetime and our attention span. But if we just zoom out a little bit, and it's pretty frightening. We're basically taking apart, it's kind of like taking apart the airplane while it's flying, and just pulling out a bolt here and a nut there, and taking off this screw and this piece, and seeing if the whole thing can still fly. Not a good idea. Okay, well, it looks like I'm out of time. So I'm going to end there. I hope you enjoyed that little lecture, and good job on the last test, and good luck on the next one. I'm going to be back in Del Rio by the time you take the next test. So maybe I'll see some of you in person. Scary. Okay, see you later.